we're thinking more about an oscillating system, and this system, just to keep things simple, consists of just a spring, a mass, and then the surface along which the mass, the horizontal surface along which the mass is oscillating. And specifically, we're thinking about the energy in this system. Total energy in these kinds of systems is just a sum of the kinetic energy plus the elastic potential energy that exists whenever the spring is stretched or compressed, plus thermal energy. Remember, thermal energy is just the total kinetic plus potential energy of all the molecules that make up the objects in the system. And we distinguish between thermal energy and other kinds of energy. The other kinds of energy we can lump together and call mechanical energy, so that you can think of the total energy of the system as mechanical energy plus thermal energy, non-mechanical energy. Remember from the previous video, we saw that when work is done by friction, work is done on a moving object by friction force, that work is negative. That means energy is taken away. Specifically, kinetic energy is taken away from the object that has work, negative work done on it by friction. But of course, that energy doesn't just disappear. It goes somewhere. It goes into an increase in the thermal energy. No, kinetic energy, some energy of the system gets moved around from the kinetic energy of the mass to the thermal energy of the mass and the surface on which the mass is moving. So that energy is taken away from kinetic energy. In other words, it's taken away from mechanical energy, a negative change in mechanical energy. As we saw last time, one way of keeping track of mechanical energy is looking at the amplitude of the oscillation. We found that the value of the mechanical energy is proportional to the square of the amplitude. So if the mechanical energy decreases, like it does when friction does negative work, takes away some of that mechanical energy, then the amplitude must decrease, or smaller amplitude, as I say here. Another way of looking at that is to just imagine that our system of surface, oscillating mass, and spring is an isolated system. So there is no work done by external forces, so there's no energy coming into the system or leaving the system. The total energy of the system stays constant. But because of that work done by friction, the mechanical energy decreases. But if the total energy of the system stays constant and one kind of energy decreases, the other kind of energy has to increase by the same amount. But mechanical energy decreasing means the amplitude gets smaller and smaller. We call this damping, decrease in the amplitude as time goes by. So a graph of position versus time might look something like this. You've got one amplitude right when the oscillations start, and then the next time the mass is at its maximum distance away from equilibrium, its amplitude is smaller. And then the next time the mass is at maximum distance away from equilibrium, the amplitude is smaller still. And every time the mass comes to a point of maximum distance away from equilibrium, that maximum distance is smaller and smaller and smaller. If we were to make a curve that matches the sizes of these amplitudes, we get, well, it looks like a straight line, but we'd actually get a curve. Let me make this more curvy by starting off higher. Like that. And the curve is represented by an exponential function. It's a good idea to be at this time to think about exponential change. In this case, it's an exponential decrease or an exponential decay, you might say. The amplitude is decaying away. Anytime you have an exponential change, the amount you have as a function of time looks something like this. Amplitude at any particular time is some constant. I'll call it amplitude 0, and there's a reason I call it that, time e to the minus time over tau. And I'll talk about what tau means later. But the idea here is that anytime you have exponential change, it's because the rate of change is always proportional to the amount of stuff that you have. Or in this case, the rate of change in amplitude is proportional to the amplitude at that moment. So as the amplitude decreases, as this gets smaller, then the rate at which amplitude changes gets smaller. And you can we can see that pretty easily if we just look in detail at a graph that shows how the amplitude decays with time. So here's amplitude as a function of time. And whenever we're talking about exponential decay, one convenient number is the length of time it takes to decrease to half of its original size. In the context of radiation, we call that a half-life. You could call it a half-life here. So here's the original value of the amplitude, and then at some time, the amplitude will have half that value. Here's half the value about here. And that happens at this time. So this length of time we can call, let's call it T1 half for half-life, the time it takes for half of what you've got to disappear. If this is the time that it takes for half of what you've got to disappear, then in this much time, from this time to this time, half of what you started with will disappear. So at this time, you've got this much, which is about half of what you had at the beginning of this time interval. And then wait another T1 half, so time from here to here. And at that time, you now have half of what you had at the beginning of that time interval. That is, after one of these half-lives, the amplitude is down to 1/2 of what it had been. And then if you look another half-life, starting at the time when the amplitude was 1/2 of the original, half of half will disappear. So at this time you'll be left with 1/4. And now, during this time, half of what you've got will disappear. So half of 1/4 will disappear, and what you have left at this time is 1/8. So you can see that basic property of exponential decay. The rate of decay depends on how much you have. Here at the earliest times you had the most amplitude, so you had a big change during this much time. And now you've got less amplitude, so in that same amount of time, you get only half as much change as you did earlier. And now, later on in that same amount of time, you end up with an even smaller change than you did in the previous time interval, which was smaller than the change you had in the earliest time interval. Okay, now let's think in a little bit more detail about using this equation. Tau, this Greek letter tau here, it's a length of time, and it's a length of time that that we use to characterize how long it takes for an amplitude to decay. But first, let's think about the meaning of this this number here, A0. At time 0, right when the damped oscillations begin, the function looks like this: A0 e to the minus time, which is 0 over tau. Well, this now is e to the 0. Anything to the 0 power is defined to be 1. So we've got A0 times 1. A0 then is the amplitude right at the start. The amplitude right at the start when the oscillations first begin. Okay, now imagine this situation. Let's say we're watching something oscillate, and we say that in 2 minutes we see the amplitude decrease from the original value to 90% of the original value. This was the amplitude right at time 0 when the oscillations start, and this is the amplitude 2 minutes later, or 120 seconds later. And that's information that we could put into this equation, and that will allow us to figure out exactly what the tau factor is for this particular kind of damping. So put those numbers into our equation, and A at a time of 120 seconds is just 0.9 A0, and that's equal to A0 e to the minus 120 seconds over tau seconds. Let's simplify this a little bit because we have a factor of A0 on both sides. Just divide the whole equation by A0, and now we've got 0.9 equals e to the minus 120 over tau. We're trying to solve for tau, so somehow we have to get tau out of that exponent. And we do that with another kind of function that's very closely related to this exponential function, a logarithmic function, a particular kind of logarithmic function that's called a natural logarithm. It's called ln on your calculator. That's the button you'll use in these kinds of situations. And this logarithm, like every other logarithm, is an exponent. What I mean by that is that the logarithm of something or other has some value, but this is an exponent, and this is just another name for that same exponent. Exponent to what base? What is it that's being taken to this power? Well, e, that is, e to the y is then equal to x. That's what a natural log means. It's a kind of an exponent, this kind of exponent, a power to which you raise this number e. Okay, so right here we have an equation in this form, right? In this case, the thing that corresponds to x is 0.9, and the thing that corresponds to y is minus 1/22 over tau. So that's x and y. Put that x in there, put that y in there, and you can find the value of tau. What that looks like is this ln of x, which is 0.9 in this case. Natural log of 0.9 equals minus 1/22 over tau, or tau equals minus 1/22 over natural log of 0.9. And this tau is a length of time, remember, so it's a positive number, and that works out. Even though you've got a negative sign up here in the numerator, turns out that for all logarithmic functions, logarithm of something less than 1 is always a negative number. So both numerator and denominator are going to be negative numbers in this case, and the negatives will just cancel out. You'll get a positive value for tau, the time. Okay, now what exactly does tau mean? How does it characterize the strength or the weakness of the damping? And we can figure that out by going back to the original equation. And thinking about what happens after the oscillation has been going on for tau seconds. In that case, a0 e to the minus time, which is tau, over tau. So that's a0 times e to the minus 1, or same thing as a0 over e, and let your calculator figure out what 1 over e is, and you find out that it's about 0.37. In other words, after the oscillation has been going on for tau seconds, the amplitude is now decreased down to 37% of what it had been originally, almost 1/3 of what it had been originally. After tau seconds, almost 2/3 of the amplitude has disappeared. And so For example, if tau is a fairly large number, that means it takes a long time to get this much decay, and that would characterize a relatively weak damping that takes a long time. Say the mass hanging from a spring and you just let it go, it oscillates for a long time. It takes a long time for that amplitude to noticeably decrease. And so that would correspond to a big value of tau. And then a small value of tau means it takes just a short time for the amplitude to decrease down to 37% of what it had started as. In other words, whatever friction-like force is doing the damping, it's a very strong force, and when it does work, it's doing a lot of work, taking away much energy per second to reduce the amplitude of the oscillation. Okay, and then just one other example of this kind of thing. Let's say we have a situation where we know what tau is. Let's say tau we know is 5 minutes or 300 seconds. And we'd like to figure out how long it takes for the amplitude to decay to 1/2 of its original size. It takes some amount of time that we're trying to figure out. After this amount of time, which we're trying to figure out, the amplitude is 1/2 of what it had been at the start. But now, write the equation for amplitude as a function of time, a0 e to the minus mystery time that we're trying to figure out, divided by tau, which is 300 seconds. And again, just like in the previous example, the a0, you divide the whole equation by a0, the a0's cancel out, and you're left with you're left with 1/2 equals e to the minus mystery time over 300 seconds. And just like in the previous example, the thing you're trying to figure out is up in the exponent, so you have to get it out of the exponent and use the same natural logarithm trick. ln of something is an exponent, which we will call y. It's an exponent to which e is raised. And if e is raised to that exponent, the number you get is whatever number was in this slot. So you're comparing this with this. In this case, 1/2 corresponds to x. And then that exponent corresponds to y, minus the mystery time over 300 seconds. So take that x and y and put it in this equation, and have the calculator tell you what the value of ln is, what the value of the natural log is in this case. So x is 1/2, so we've got ln of 1/2 equals y minus t over 300 seconds. Or multiply both sides of the equation by minus 300 seconds. And you've got here minus 300 seconds ln of 1/2 equals the time. And again, this is the log of something less than 1, so it's going to be a negative number. Negative times the negative will give you a positive value for time. That's what you have to have. Natural log of 1/2 turns out to be about .693, or negative 0.693. So that 300 times that is the time. I don't have my calculator with me, but that's a small detail. Now you see how to figure out these things. Okay, so that's how exponential change happens. We'll see that a few more times in the next few weeks. The other oscillation-related topic that we need to introduce right now is resonance. That'll become very important when we start thinking about sound and sound waves. But the idea of resonance is fairly easy to understand. You've got an oscillating system which has a normal frequency and a normal period. If you started oscillating, you'll always get that same frequency. You'll always get that same period. For any particular value of spring constant K and for any particular value of mass, that determines the period and the frequency. And no matter what you do to start the oscillations going, the mass will always oscillate at that one frequency. And we call that the natural frequency, the frequency at which the object naturally oscillates. But you could periodically give the mass a push. For instance, if a little kid is on a swinging back and forth, every time that the kid comes down to the lowest point in the path, you give the kid a push. So the kid is swinging back and forth at a particular frequency, and because you always give the kid a push in the same situation, you give the kid a push every time the kid is going this way and gets to the bottom of the path, the frequency of your pushes is the same as the natural frequency. But of course, you could push at any frequency. Usually we call that a driving frequency. And the idea of resonance is that amplitude in an oscillating system depends on the driving frequency. If you got some external force pushing that oscillating system around, the relationship looks like this. Plain old F is the driving frequency, the frequency at which the external force gives the oscillating mass a kick. Here's the natural frequency. And for most values of frequency, of driving frequency, you don't get much of an amplitude at all, but right at the driving frequency you get the biggest possible amplitude, and at frequencies close, when the driving frequency is equal to the natural frequency, you get the biggest amplitude. When the driving frequency is close to the natural frequency, you can also get some big amplitudes. And why is that? Let's go back to the kid on the swings, and then you're giving the kid a push. So there's the path of the kid, and then when the kid's going back and forth, and then every time the kid is at the lowest point and moving this way, velocity in that direction, you give the kid a push in that direction. Right? Your external force is is in that direction. And let's say the frequency of your pushes is the same as the natural frequency. That means every time the kid is in this state, you'll give another push. And this is the only situation when you will give the kid a push. So that means every time you give the kid a push, because the frequency of your pushes is the same as the natural frequency of the kid, in this case, you'll be giving the kid doing the maximum amount of work, the maximum possible amount of work for the kid. Right? The work in this case is just the strength of your pushing force times the distance that you push, the distance that the kid moves while your hands are pushing, times cosine of the angle. Remember that angle in work is the angle between the force direction and the displacement direction. Well, the kid is moving this way, so displacement is horizontal to the right, the force is horizontal to the right, so the amount of work done is that's a cosine of 0, and the cosine of 0 is positive 1. Positive 1 is the largest value that cosine can have. So this is the largest amount of work that you can do for that kid. Every time the kid comes down to the bottom of the path and you give the kid a push, you're doing the maximum amount of work. That is, you're giving the maximum amount of energy to the oscillating kid on the swing. Doing positive work gives energy to the thing that's having work done on it. So, giving the kid lots of energy because you're doing lots of work on the kid, that means the mechanical energy of the system has increased a lot. And remember, mechanical energy is proportional to the square of the amplitude. So if you have a lot of mechanical energy, you get a big amplitude. If the frequency of your push is not the same as the natural frequency of the kid on the swing, then you won't always push at this time. Sometimes you'll push to the right when the kid is moving to the right, and that'll give you positive work, like in this situation, but at other times you'll push to the right while the kid is moving to the left. And what happens in that case? Right, obviously you're going to, in pushing against the kid's motion, kid's going to slow down because negative work is being done. But let's just go through the steps here. In this case, the work done is magnitude of the force, magnitude, size of the displacement, the distance traveled while you are pushing, times cosine of the angle between force and displacement. Well, now in this case, the kid is moving this way, so the displacement of the kid is this way, but the force, your push, is in the opposite direction. So they're 180 degrees apart. And the cosine of 180 is -1. And of course, when you do negative work, you take energy away. So in other words, if your driving force, that is, your pushes, are not at the same frequency as the natural frequency of the swing, sometimes you'll be pushing in the correct direction to do positive work, but at other times you'll be pushing in the wrong direction and do negative work and take energy away. And if there's too much of a difference between the driving frequency and the natural frequency, if there's too much of a difference between the natural frequency and the driving frequency, then whatever energy you might give at one time gets taken away, in the next push, and so overall you're really not adding to the mechanical energy of the kid and the swing, so you're not increasing the amplitude. And resonances we introduce now, but they'll become very important when we talk about sound and sound waves.